Hello, and let's have some blue fun this week. I would like to welcome you on lesson 4 of schematic and PCB design course. This week we are going to speak about footprints, 3D models, and how to start your new PCB. Before we start, I would like to motivate you. I would like to show you what you can achieve in very short time, as I have very good example. Friend of mine, his name is Rafael, so say hello to Rafael. He started using Altium Designer just 5 months ago. He's 18 years old, 1-8, and he has designed his own board, which is used for robots. And Rafael goes with these robots to plenty competitions. So have a look how his 3D model of his latest robot look. That's really great. I think it's really very nice. I love this 3D model. It's like, wow. Yeah, 18 years old, just few months with Altium Designer. So you can do it too, and I'm pretty sure you now see where I'm going with why 3D models are so important, because even in this case it helps a lot when you can visualize how the board will look, and it will help you to design a board which will fit perfectly to your system at first time. Let's summarize what you were doing the last few weeks. You imported reference schematics, you connected reference schematics together, you put everything else into your schematic, everything what was in specification, everything what we were speaking about some time ago. When you need to make decision, put it there, don't put it there. Don't waste your time with making the decision, always put it there. So your schematic is now huge, there is a lot of things, but it's almost ready. You also replace all the schematic symbols with the symbols from your library, and that's why the schematic is in preliminary stage. And what you need to do now is you need to see if everything actually fits on your board, because the board shape is many times defined. It is defined by enclosure, by system where the board is mounted, or by specification, form factor, or I don't know, anything else. So your components may not fit on the board. And now is the time when you sit down with your boss, with your client, you use the 2D or 3D model of your board and see how it fits, where you can place the key components, and if something doesn't fit, now is the time to make the decision what is going to be removed from the schematic. And the 3D model is not only to make it nice. No. It actually visualize your work, what you've been doing for a couple of last or past weeks. It is a lot of work. And your boss, your client, can see what you were doing. That's one thing. The other thing is mechanical part of your design. It's as important as the electrical, because You know, if two components collide together and you can't fit them on the board, you have to redesign the board. If the board is, or if the component is too big and you can't fit your board into enclosure, you have to redesign the board. It is almost same like make electrical mistake. You cannot use the board. So it's really important to see how the board will look. Let's do it. Let's create a simple resistor footprint just to show you how easy it is, and also it is part of this lesson, so we need to go through this process. I will create PCB library and I will use component wizard. So I select resistor and millimeters. I want SMT. I know these dimensions from datasheet. I just move it. I delete this because there are two parts of the line. I just simply copy and place that this one and put it here. Few words about what we can see here. On the bottom there are different layers. For example, top layer is the top copper, the bottom one is same but on the bottom side of the PCB. Top overlay is this yellow one. It's actually on the PCB it is usually the white color which is around components. Bottom overlay same just for bottom side. Top paste, this is where the tin is going to be placed during the board assembly, and here it is simple. Usually it is just around the path, but for some components, for example here, you can see you can make a special shapes of the tin if you need. And same for the bottom. Top solder, it's on the PCB usually there is a green color on the top of the PCB, so this solder defines the space without the green color, so it's usually where the paths are located. Same for bottom, I don't use these others. Few more things about footprint. There is a reference point which specify component location when pick and place file is generated. This file is used by machine which pick component and place it somewhere. So if you have never been thinking about how this point is used, or you maybe even didn't know it is used, for SMT components place it into middle. You can do it here. For through-hole components which are placed manually, I normally use reference point in pin 1 because then it's easy to put their dimension on your PCB and tell the other people who, for example, design enclosure. You can tell them where the connector is located, and then they can make a hole in enclosure exactly based on this dimension. It is easier than if you place it into the middle of the component and the pin 1 will be somewhere which is very hard to measure. This is just 2D, I show you. Now I press number 3 on my keyboard. There is no 3D model of this component. Press number 2, go back here. To create a simple 3D model is very easy. Just depends what you need. This is standard square, which I'm going to draw now. This is the color, and this is the height. And I will draw it. Just give you an idea how it can be done. Now have a look on the 3D model. See, we have there our resistor. You can simply make it look nicer. I can, for example, move it. Oops. And place there something else but the different color. I will copy it, Ctrl C, Ctrl V. Now when I press number 3, I'm holding down Shift to rotate with the component. Yeah, very simple, very, very, very simple. We are almost done. There is one layer missing, but I will speak about the layer a little bit later. You need to understand why we need to create it. What we can do now is we can save the library. Okay. We can go to our schematic library, to our resistor, which we created last week. And what we have to do to complete the component, we need to add footprint. So the physical interpretation of the component. And we will add the footprint which we have just created. So use the my library, and here is our footprint R0603. Great. We can now use this component in our schematics. If you have already used this component in your schematic, you will need to update the schematic symbols in your schematic. Simple way is just press right click and update schematic sheet. If you have it in schematic used, it will update it, and all the components in your schematic will also now have this information about footprint. So we go back. And I don't know if you have noticed, I use R for this resistor footprint, and I use C for components footprints. Do you know why I use two different 0603 footprints? Yeah, it's simple. First, I can use different 3D model. I can use black 3D model for resistors. I can use yellow 3D model for capacitors. So the board looks more real. The second thing is there is a little bit difference between capacitor and resistor footprint, because capacitors are taller, so they need a bigger path than resistors. Life would be too easy if everything is so simple. So we need to also speak a little bit about how to create a difficult component, and this is one of the reasons why many people doesn't want to create their own libraries. Sometimes it may be quite a lot of work and time consuming, but it has to be done. So let's speak about my example, which is this SO dim slot, and we are going to create footprint for it. I will split my screen. You can see now both libraries. I could simply just copy and place this component to my library, of course, but then you wouldn't see how you can create your own difficult footprints. I always start with component wizard, because from these few options what are here, you can actually start any kind of component. In our case, this is pretty similar to SOP footprint, so I will start with SOP. I will use millimeters. I know this from datasheet. This is 6, okay. Just press next, next. Name it. And it doesn't look like our component yet, but we already done a lot of work. Everything what we need to do now is change the path to be square. It can be done in one step. I will press Shift S to work only on one layer. I go to this inspector and change it. Yeah, it changed for all selected paths. If you don't have this inspector, you will find it here in this bottom right corner. You need to turn it on. What we need to do now is we need to move this second row a little bit lower. You can see it here, it's not on one level. For this I need to check if I'm using metric, okay, and I need to check my grid, because I want to have step 0.1 millimeter. It's correct. So I can select all the pins in this second row. Now I will be looking here in this bottom left corner, where position of the cursor is always shown. I will be looking on this Y position. I will use this move command, click here and press arrow down, 1, 2, 3. Great. It's in right position now. And to make it look like our connector, we need to remove these few pins. So I don't want to count them, I just will measure it. It's faster, so I will find the position of this path. It is 21 millimeters down. So I go to my component and I will be looking for path placed in position -21. It is this one. So I need to remove 4 paths here. Press delete, hold shift down, press delete. Wow, almost done. What we are missing are these 4 other paths. I ignore these 4 other paths. Just place a path, or you can just simply copy and place it. From datasheet you will see what are the dimensions. So 4.6, 3.5, 4.6, 3.5 for the hole. This is actually a special hole because it is not plated. It's a hole. Not plated means that there is no copper in the hole, so there is no connection between top and bottom layer. 1.6 millimeter. 1.6, not plated. There is no ring around the hole. And position. We need to place it into the right position. So I will measure it again, but you will need to read it from datasheet. 4.1, 1.75. 4.1, 1.75. Okay, for this one. Oh, for this one we need to measure it again. So, okay, 16.1, 1.15. You are clever, yeah? You know how to continue with this. It's almost done. Now everything what you have to do is just finish it. Also draw this outline the way it needs to be done. And very, very, very important thing, pin numbering. Have a look on our pins. You have it like 1, 212, 2, 211. That's not correct. It needs to be 1, 2, 3, 4, 5. This is actually one of the most common mistakes in libraries. Check your pin numbering according to datasheet and according to schematic symbol. Because, for example, in schematic symbol, I'll show you. In schematic symbol for this hole and for these other parts, you see it is MP1. Yeah, it's this part. I always place all the other parts also into this schematic, and they need to be correct. You know, if you have, for example, just a week ago happened to me, a friend of mine told me, oh, I made a mistake. I used a switch with 4 pins, and you know, the switch was connected between 2 pins, of course. And what happened is it was not correct, because pins in the schematic were like, for example, 1, 2, 3, 4, and pins in the footprint were like 1, 2, 3, 4. So it was wrong. Always be sure pins in the schematics are exactly like pins in the datasheet, and pins in your footprint are exactly same in your datasheet. Many mistakes happen like this. So correct the pin numbers. 2, 3. You got the idea, yeah? You know what I mean. You know what? Let's take a short break. Go away for a little bit from all these footprints and 3D models. And I was thinking what could be interesting for you, what is not normally on internet, not many articles about it. And I went back to the PC. If you've been ever thinking what is actually in your PC, what is on the board when you take the motherboard, what are the chips, what you can find there? Did you try to find the question? Have you ever heard about South Bridge, North Bridge? So let's have a look what's there. This is a VIA chipset, and typical 3-chip solution. That's actually one of the reasons why x86 is so expensive, because you need to buy 3 chips minimum. Of course there are plenty others, and there is why it is so power hungry, because you have 3 chips which are quite power hungry, each of them. First one is processor. It is separated because you can have faster board, you can have slower board, you can have more expensive board, you can have cheaper board, so it is separated. These 2 chips are fixed, they are soldered down on the board. This is the NOR bridge, which integrates memory controller, and the memory is connected to the memory controller, and it has also integrated graphic, so monitor and displays connects them. South bridge, it has all the other peripherals like SATA, audio. This is actually interface, you need another chip for audio, yeah. Then USB, PCI, LPC, and LPC, that's quite characteristic for x86. It is used, it used to be used for BIOS a lot. Now the BIOS has been moved to SPI interface, and the Super I/O is connected to the LPC bus. Super I/O is the chip which supports usually serial ports, and you can see it here, the parallel port, floppy, but today mostly serial ports are used from the Super I/O. It has also some kind of power management and power monitor to monitor temperatures, control fans, and monitor voltages on the. It has very good BIOS support, so it is still used a lot in designs. So this is 3-chip solution. This is 2-chip solution from Intel based on Intel Atom board. So this is Intel Atom processor, and they don't have, you see, there is no NOR bridge, South bridge. They call it system controller hub. There is integrated graphic, and the memory is connected to this controller hub. Also displays and monitor connects to the graphic, and all the other peripherals. You see, again, audio interface, you need external audio chip, USB ports, PCI Express, that's different to the VIA chipset. The VIA chipset was a little bit older. IDE, so here is no SATA, and some other standard stuff. As you can see, this is packed together, so it is for smaller devices, and there is not really much on this controller hub. This is a different Intel chipset. It is Intel Core processor, and this is interesting. See, the processor is integrated with graphic card, and then there is the second chip. Why to integrate processor with graphic card? What do you think? What could be the advantage? No, there is advantage which Intel use on if it's supported, and the advantage is in sharing power between processor and graphic. What it means, if you have a CPU hungry application, so you know you have one heatsink, you have one power dissipation from the chip, maximum power dissipation, and the graphic, if graphic doesn't work on full power, processor can actually work on little bit more power, and when processor doesn't work on full power, so graphic can work on full power. So for example, let's say if you have 10 watts or 20 watts of total which you can have on this processor, so you can work like 10 watts for processor, 10 watts for graphic, or you can have 15 watts for processor and 5 watts for graphic, or the other way, 15 watts for graphic and 5 watts for processor. That's quite interesting. Second chip doesn't have the graphic card because it is here, but there is a special interface which connects with the second chip, and displays and monitors connects to the second chip. SPI flash, as I mentioned, BIOS is now in SPI flash because it's a much smaller chip, and the interface, the bus is really simple comparing to LPC. Super I/O option on LPC, again PCI Express option much more than it was before. Ethernet, audio, again this is audio interface, USBs, SATA. This interface is usually used to read the temperatures. This one is AMD processor with integrated graphic, memories connected to the processor, graphic interface directly to the processor. So you see, each of them, they are different, but again this is two-chip solution. USBs, SPI for BIOS, LPC for Super I/O, all the other standard things. Ethernet integrated in this chip, in this controller hub. You need only PHY, you don't need the complete Ethernet. Audio codec, SATA, PCI bus, PCI Express. So each PC is different, but you can see mostly 3-chip solution, 2-chip solution, 1-chip solutions exist, and it depends on what chipset it is used, and if the application is your laptop or it is your desktop PC. But you now have an idea how it looks there, what are the buses, what are the interfaces on your board, what the additional chips are doing. So I hope it was useful for you, and let's go back to the footprints and 3D models. We know how to create a simple 3D model, and it is much better if you can find existing 3D model, because it will make your board look much more real, and they are available for many connectors. The manufacturers, they provide the 3D model, so it's quite simple. Just download the 3D model and use it. I'll show you how. I go to the library where we have the connector, and I will check manufacturer and the part number. I copy the part number, go to the TE connectivity website, and I will find the slot. Here is the 3D model. We need the step file, so download it. And I downloaded it here, so I go, this is the step file. I go to our lesson 4 course, design files, Altium files, library and 3D models. I will copy it there. Go to our component, place 3D body, step model, embed step model, select the model which we just copied there. Yeah, it is in lesson 4 3D models, and place it. Press number 3. It needs to be corrected, so the rotation I will change it to 90, and press spacebar. And if you have a look, we need to also put their offset because the pins are not on the paths. So So the offset is 2.7. Now it's correct. What I have to do, I just need to place the model on my paths. Almost. Okay. 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 Now we not only have the 3D model of the component, but we can very easily check if our footprint is correct. This is very important because otherwise you may need to have the 3D model, the footprint physically. What we can do, we can check, for example, if the hole is correct. Yeah, is the hole in correct position? Perfect. We see, you know, all the paths are correct. Only maybe what we want to do is the outline. So I go to this 2D view and I make it wider. Wow, wasn't so difficult, yeah? And you have very nice connector. And what is great, when you have all the components like this, you can very easily to create 3D model of your board. That's what we are going to do now. This is going to be very difficult, so please watch carefully. To start your own PCB, you need to have schematic and PCB library. So we need to generate it. You know how to create the schematic library. We have it. Same way we will create library from PCB. This is very powerful tool because if you have a reference design, you can create your PCB library from the reference design, so you don't have to create all the footprints by yourself, especially for difficult footprints like processor footprints or this kind of thing. You don't have to create them. You just import it to Altium and create the library. And from this library you can simply just go and copy any component what is here, copy, you know, go to your own library and just simply place, tada, so copy footprints from reference boards to your own library. Now when we have libraries, I will remove this PCB because we are going to create a new one. I will close this. Just make it simple for you. Okay, we have schematic, we have libraries, and we want to start a new PCB. We add the new PCB file. I will call it somehow like test file. Yeah. I will draw a shape of our new board. I will use big grid and use design board shape, redefine board shape. You can change it later, no problems. I'll just do it like this. Great. Now this is the command which transfers all the components from your schematics through the libraries to the PCB. It may take some time because it's quite a big project. When it imports, you will have the area for your board and a lot of components out of this area. What you need to do then is just pick the components and start placement. Yeah, and you will see, because the Voipack board, they don't have 3D models, you will see there is no 3D model of the board yet. We are going to try it, how to make it 3D. So let's go to the PCB. Here we go. Here is our board. You can redefine it anytime to any shape you need. And here are the components. So let's say this component is going to be here, and this is going to be here, and this one is going to be here. You got it, yeah? I'll show you the 3D model. See, there are no 3D components. I can hide the connections. No 3D models. You know how to start your new PCB. At this moment, I will just switch and use the Voipack existing libraries, so we can continue, and I can show you how you can add 3D models to this Voipack library, because this is going to be your task for this week. You don't have to do it for everything, but practice, practice, practice. Yeah, it will help you. What I will do now, I will close these libraries which we just created for this test. I will remove it from the project. I will also remove this our new PCB. We don't want it. We don't need to have it here. Close it, and I will add these are the existing libraries, the Voipack libraries, and this is the existing board. Now I show you how you can add the 3D model to the Voipack library. See, there are no 3D models on this board. Go to the library, and we will pick a component, for example this one, where we are going to add the 3D model. It's pretty simple. As we said before, we just draw a simple shape. It is going to be our new 3D model, and I will update the PCB with this new footprint. Check which layers you need to update. Let's have a look on the Voipack PCB. here we go, there is the 3D model. So everything what you need to have nice 3D model of your PCB is to add the 3D models for the components in your library. Very simple. The results are great. As you could see on the Raphael's example, and they are very helpful. Your eyes are closing, you want to sleep, you are not tired. I'm kidding. I understand this kind of a lesson may be difficult for people who are new. You know, if you've never done anything in Altium Designer, it's a lot of information, a lot of new things. And on the other side, if you already know all the things, it may be a little bit, you know, too slow, maybe. So I was thinking, you know, about this iron. What do you think why I have it here? It's a bonus time, yeah. When I was starting, like in 2002, with BGAs and all these things, it was very expensive to assemble the board. So we were assembling all the boards at home or in the company. And what we used to do, we had iron and we placed small nuts on the iron, yeah, like this, and then we put our PCB on the top and big nuts around and another iron on the top. So there was small gap, and we were soldering the BGAs this way. I don't know if it's still possible with lead-free parts, because the temperature for lead-free part is higher than for leaded. But what I know, we didn't use the steam. That I'm pretty sure about. These days there is a much easier way to remove or solder down some components. Normally what we use are hot air guns. You don't need anything special like this. We use a lot something simple like this, for example. Desolder, very easy. You know, you have your PCB, you take the gun and go closer, closer, closer. Wait, when it's hot, remove the chip. Similar, when you want to solder it, I solder many chips with this kind of gun. For example, I use it a lot to change a package which has pad on the bottom and it's QFN. No. So how you do it? You place a little bit of tin on your PCB, not much, just a little bit. Also put it around on all the pads and in the middle. You will need something like this, flux. You need to put it there, not too much, because if you put there too much, the component, when the flux will be vaporizing, the component may move. So not too much. Put it there, put there the component, take your hot air gun and again go. Put it on like 400 degrees and go closer from like 5 centimeters or 10. Go closer, 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 closer to like maybe 2 centimeters and wait and watch. You will see when the tin melts you will see the component moves a little bit and then it just goes down. You will see it. I'm pretty sure you will see it. Just watch it. And then when it goes down, still wait a little bit, and then you can take off the gun and just cool down your PCB. For QFN packages, I also then go around the chip. Again, I use the flux, put it around the chip, and go with the standard soldering iron around the chip and solder all the pins around. So I hope you don't sleep now. Of course, we don't use irons and hot air guns to solder products. That's not possible. But hot air gun is quite useful in lab, so you can try it. And this could be actually the challenge for this week. Find an old board and you can try it. You know, you can try remove the QFN package from old board and maybe try to solder it back. Just get some practicing. You may use it on something more important later when your important board comes in and you need to quickly replace a chip, so you can then use the hot air gun. Practice this week. We have one more thing to speak about this week, and actually not many engineers use it, and many of them, they don't know they can do it this way. And the topic is about assembly drawing. What is it and how it is used? If you have a simple PCB, you can put the references, you know, the text which describes what component, where it is placed. You can place it on the PCB itself, on this top overlay layer. It's the white color, you know. But for things like this is one of the boards what I designed, and have a look on the bottom side. Yeah, there is no space. How do you identify the component? When you send into production this kind of board, how they can check the position of the component? They need something to tell them where each component is located. That's the assembly drawing. It looks like this. Yeah? And it can be very easy done in Altium Designer. I'll now show you how to create these layers. First, what we have to do is specify the layers where these assembly drawings will be placed. So I go to the Altium Designer and I will enable, usually I place it on layer 29 and 20 and 30, so I will enable them. And now I need to create a pair, because there will be, we will specify only one layer in the library, you will see, but both layers will be used, depends if the component is on the top layer or on the bottom layer. So we have to specify layer pair. Okay, now we can go to our library, and let's say we will create the assembly layer for this component. I will enable the 29 also here. You can use any other. I go on the layer 21 and I will draw a line just around the component. Okay. Also, I would like to have the reference designator inside, so I will place the text here. but we need to tell this is not actually something simple, it is dynamic. So based on the reference designator, it will automatically change. I will change the font to be smaller so it fits here. Okay, now I can update this footprint. And let's have a look what happened. See, we have here the component, and we need to set one more thing. It's convert special strings. Ta-da! If you do this for every component, you will have very nice assembly drawing on, and it's created automatically, no problems. So I'll just demonstrate for something else, something like this one again, yeah? For example, I will copy this text, place it on layer 29, just draw the line. Don't forget, on layer 29, we are drawing on layer 29. Update it on PCB. Have a look on our PCB. Yeah, you got it. You understand. Automatically, if the component is on the bottom side, you will see it on the bottom side. And this is what we would like to achieve. When you create the assembly layer for every component in your library, your board will look like this. This is actually the Wojpak module which we are going to use when we will speak about memory layout. As you can see from the bottom, it's automatic. So there is a lot of work for this week for everyone who is working on his own project, her own project. Create footprints for all your symbols, add 3D model for all your components. If you don't have your own project, do it for Wojpak, but you don't have to do it for everything because there is a lot of components. And create assembly layer for all the components. Practice, practice, practice. You will remember it better, and your project, again, you will move ahead in your project. Your project will look much better. And I'm really curious about your 3D models. Send some 3D models or share them on Facebook, for example, to show other people how your 3D model looks. This was a quite difficult lesson. Next time it will be about something new, about something what not many people use it this way. It's about variants and about the bombs, which we were speaking about in the lesson where we were creating the libraries. So we will now use the information from the library and generate really good bombs. You will like them. So thank you very much for watching this week, and see you next week. Bye bye.